So now that we have discussed what is necessary to establish a causal relationship and have knowledge about the threats to validity, we can finally start to talk about implementing a design. There are three ways to classify a design: a randomized or true experiment, a quasi-experiment, or an observational study. If random assignment is used, remember that's just how you assign the groups to either treatment or control, then you have a true experiment and you can establish a cause and effect relationship to a very high degree of certainty. If you can't randomly assign groups, then you have to ask yourself if you have a control group or if you have multiple measures of the dependent variable. By the dependent variable, I mean your outcomes, the data that you're collecting. If the answer is yes, then you have a quasi-experiment. If not, then you have an observational study. The degree to which you are able to establish a cause and effect relationship in a quasi-experiment often depends on your ability to show that the groups are still relatively equivalent or similar. The more you can show or argue that the groups are as homogeneous as possible, the higher the internal validity. That's why some pre-measurement is usually needed in most quasi-experiments. I will now discuss the three most used designs in education. Every single one of these designs are classified as quasi-experimental. This is because true randomization is often difficult to achieve for several reasons. First, we often apply a treatment group to an entire intact class, and then we collect data on individual students. This could be because it's convenient, less disruptive, less time consuming, or more cost effective. Here at Primavera, you also don't know your population in advance as new classes are assigned each term. So any study that extended beyond one term would be hard to randomly assign. So the first group here is called the non-equivalent group design. This does not necessarily mean that the groups are not comparable or similar. In fact, your goal is to try to make them as similar as possible. It just means that the groups are not statistically guaranteed to be as similar as they would be if we assign them through a random lottery. This design is a true group pre-test post-test design. The N in the table here means that the groups were not assigned randomly. There are two rows, one representing each group. The O's represent a measurement that is made, and finally the X indicates a treatment. So in this top row, we have a group that was non-randomly assigned. It was given a pre-test, a treatment, and then a post-test. Time is moving from left to right here. And in the bottom row, we have a non-randomly assigned group that was given a pre-test, no treatment, and then a post-test. So this is the control group. Since groups are not randomly assigned, you must take measures to avoid selection threats. By analyzing the data in a similar fashion to what's shown to the right, you can actually determine if a particular type of selection threat occurred. Recall that it's the pretest that makes this possible. Since we want to show that the two groups were similar, we would like the pretest results to be statistically the same. You could do this by using a hypothesis test such as an ANOVA or a t-test. We won't discuss how to do that in this session, but it will be discussed in a future session. So if I take a look at this graph over here, we have the X's, those are the treatment groups, and we have the O's, those are the control groups. And then we have both their pre-test and post-test plotted on a scatter plot. So one thing that jumps right out without even doing statistical analysis is that there's a major jump or a treatment effect here because all the X's seem to be higher. And you could look and see that the post-test average was 15 points higher if you look at between the treatment group and the control group. If you look at the pre-test, you would see that the O's, if I kind of look at what's the middle of this green patch of O's, it's at 50. So their pre-test average is 50. And their post-test average is about 50 as well. So they didn't really improve, whereas the post-test average on the treatment group is 65. So as what I would do, I would want to make sure that I could argue that the two groups were basically equivalent. So if I have enough data points here, I could look at the pretest and I can see that the treatment group, you notice how it's shifted to the right a little bit, actually had a 5-point advantage. Their pretest average was 50 and the treatment groups was 55. So using statistical analysis, you could actually determine if those two means happen by chance, if they're actually the same or if they're truly different. So here I might be concerned a little bit about a certain type of threat. Maybe the groups weren't as similar as I thought to begin with, even though I see this giant treatment effect. The next type of design is called the regression discontinuity design, and it has a name that in everyday language implies something negative. However, in research, this design is one of the most useful to us as educators. In fact, this design began being used in the 1970s when it was incorporated into the nationwide evaluation system for educational programs funded under Title I. So it came about due to education, and this is how programs are evaluated in education. The design is a two-group pre-test post-test design where the participants are placed into a group based on a cutoff score on some pre-test measure. The main advantage is that the treatment or intervention is then given to the most needy students. You don't want to deny it to those that need it most. As such, we don't run into any ethical concerns related to denying an intervention to students that need it most. So basically what you do is you decide what an appropriate cutoff score is on some pretest or some pre-measure. It does need to be numerical and it needs to be continuous, so like on a 100-point scale. It doesn't have to be 50 points like shown below here. It can be anything that you decide is appropriate. Maybe an appropriate cutoff score is 40 or maybe it's 60. All right, so then is what happens is the students that get the cutoff score, they're below the cutoff, are assigned to the treatment group. And the students that score above that cutoff score are assigned the control group. So you give them the pre-measure. Then using that pre-measure, let me go back to the slide, using that pre-measure, you assign groups. And then finally, you give them both a post-test. So obviously, we talked about some of the pros here to doing this. And some of the cons are that in order to get the same kind of statistical accuracy you would with a true randomized experiment, you need a larger sample size. So we already discussed that pre and post measures must be numeric and continuous. Now, at first glance, this design doesn't seem to make much sense, right? Because in most research that we want to do, we try to make the groups as equivalent as possible on the pre-test, and then that way we can attribute any observed change on the post-test to our treatment or intervention. But in this design, the groups are deliberately and maximally different. We said we're going to take the low students and give them the treatment, and the ones that scored above were not. It's this deliberate difference in the groups that actually contributes to why it works. But to fully understand it, you need a background in statistics, specifically regression analysis, and that's not the point of this particular um, lesson. An easier way to think about it is this. Okay, so we assume that if we assume that no treatment was given, then the pre and post relationship between the two groups would be the same. So what I mean by that is, say the poor performing students increased by 10% from the pre-test to the post-test. We hope that maybe the higher performing students would also increase by that 10%. That assumes a linear regression. Just for simplicity, we will assume that linear regression. So in relative terms, not absolute terms, they are the same. Then a program effect is determined not by comparing post-test averages, but rather a change in the pre-test or post-test relationship at that cutoff score. Okay, the reason this design can be as powerful in terms of internal validity as a randomized experiment is the fact that all validity threats would need to induce a discontinuity or a change at that cutoff score, and this is an extremely unlikely scenario in most studies. So let's take a look at how you analyze it briefly. All right, so I've collected my scores here. Notice that, yes, the lower performing students are still on average scoring lower, right, than the students that are not in the treatment group. And this is what data might look like if no intervention was administered or if the intervention had no effect. We'd assume that same type of relationship, or the rate at which they improved from pre-test to post-test would be about the same. Now, this is what a treatment effect would look like if there was a 10-point improvement. So notice now how all these blue little X's here jumped up. So if I draw the regression lines, remember that's like a line that's representing the average of all these points through here. And again, in a future lesson, I'll show you how to do that on Excel. You can see that now it's been shifted up. So basically, if there is a treatment effect, there will be a discontinuity, that means that jump, in the regression line at that cutoff score. And that's why they call it the regression discontinuity design. Finally, we have the single subject design. And this is where the individual student serves as their own control. And it's used primarily as analysis of behavior. So in education, it's used a lot in the special education setting where you're working one-on-one with students. So the pros are that the groups don't have to be chosen in advance. Well, it's just good, right? Because we often don't know who our students will be in advance. And the data analysis is relatively easy. Is what you do is you have to establish some baseline with the student. So that's one of the cons, right? Because you need to be able to measure that student over time with no treatment. Then you give them the treatment and you're hoping to observe a change. And then in this design here, they took away the treatment and just to see if the student would return back to the baseline measurements. Right, so to get any kind of true validity off of this, you need to be able to replicate it. So the more times that you can repeat it with more students, the better the validity will be. But generally, this type of design has low external validity, right? You can't apply it to a lot of students outside of your study. And to get better internal validity, you need a lot of replication. So good experimental designs have the following characteristics. They are grounded in theory. So you want your study to reflect the theories that are being investigated. And also, if you base it on theory, you'll be able to look at what somebody else's research is, look at the variables they studied, and then that will give you ideas on what you can do in your study to show validity. Good studies are also situational. That reflects the setting of the investigation. So we consider the terms, the classes, and the students as part of our design. They're feasible. Obviously, you want to be able to implement it. Consider the timing of events, problems with course assignments, student dropout, other measurements. They're redundant. They have some flexibility. Something always goes wrong. You don't want to put all your eggs in one basket. And finally, they're efficient. So you strike a balance between redundancy and over-design. So yeah, you want them to be redundant, but you also want them to be efficient because your time is valuable. Now I'd like to take a look at the last little part of our worksheet. So after I identified the threats to internal validity, external validity, and construct validity, I went ahead and edited the groups. This is kind of like a cyclical process. So I thought about the threats, and then I went back and I said, do I need to change my population of study? Do I need to change how I assign the treatment and control groups? And in this case, I decided to change my study, how I assign the treatment and control groups. I decided that due to ethical concerns, I didn't want to deny the intervention to some Algebra 1A classes and not others. So I decided to use a cutoff score to assign the students to an intervention or not. So it's basically that regression discontinuity design. I didn't think I needed to change any of the variables, so I left those as no change. And then I chose that regression discontinuity design. Finally, now we can write a SMART goal and our action steps. When I'm writing a SMART goal, I want you to concentrate on the process and not the results. One of the founding principles of any social research is that you focus on the process since the results cannot be known in advance. So when I rewrite this, notice that I'm telling you what I'm going to do and not what I'm going to improve and by how much. So I say that I will provide modified instruction based on formative assessments to Algebra 1A students that score below 50% on an exam or project. And then I like this keyword here, I will study the impact of this instruction on exams and projects. Did not say I will improve project scores or exam scores by X%. And then finally, when you write your action steps, that should just be how you're going to operationalize your research. So what you're going to do. So first step should always be research. You want to research, that's even going to give you an idea of what the variable should be and what you can implement. And then I went ahead and I talked about how I was going to implement it, how I was going to assign the students to the groups, and what data I will be collecting. Then that way there's no question at the end about what I will be doing and how I will be doing it.